にちは。今日は天ぷらかわい寿司、照り焼き、ディフェレンシャルエクエーション。ディフェレンシャルエクエーション、たこ焼き、刺身、キッコーマン、焼肉です。いただきます。
Matcha toke-toke o ramen ko da differential equation naru wasabi desu.
A differential equation is an equation na parang nilagyan mo lang ng classification. Parang differential, adjective.
Kasi, di ba, sa differential equations, pinipilit mong tanggalin si x. Yun. So that's the most different thing about differentiation.
Differential equations pwedeng ordinary, pwedeng partial. Sana grades ko may partial.
What are differential equations?
Well, they're not the same as the original function.
Hindi ko alam kung paano gamitin yung differential equation sa series.
Kasi may followers sila, mga ka-DDX.
Let's begin. So, what exactly are differential equations? Well, they're simply equations that contain derivatives. Some examples include y prime equals xy squared plus 3 and f prime prime of x equals x plus 2y. Well, f prime prime of x is also, y prime prime. Well, they might look a little weird, but think of them like regular algebraic functions we know. Whereas solutions of algebraic expressions are actual values, solutions of differential equations are functions or a set of functions. Since differential equations involve derivatives, they involve rates of change. One key in constructing the differential equations from a scenario is looking for the variable that is changing. After identifying the changing variable, we can express it in terms of the others or itself. For example, an object of mass m equals 5 kilograms is falling towards Earth with drag proportional to its velocity with a drag coefficient of 2 kilograms per second. Construct a differential equation for the velocity v. How do we get the equation for this? According to Newton's second law of motion, force F is equal to the product of mass m and acceleration a, so F equals ma. In this problem, the acceleration is the gravitational acceleration g, which can be obtained by getting the derivative of velocity v with respect to time t, so that's dv over dt. The drag slowing the object down is 2v. With these, we can obtain a differential equation for v, so that's m dv over dt equals mg minus 2v. Now, let's try verifying solutions to differential equations via substitution. Let's suppose y prime equals 2y. Which among these three equations is a solution to this differential equation? Let's start with number 1. Y equals square root of 2 ln x plus c. If we get the derivative of that equation, we get 1 over x square root of 2 ln x plus c. Next, we get the derivative of c e raised to x squared. Apologies, c should not be raised to e raised to x squared. But anyway, we get 2c x e raised to x squared for that one. Lastly, for ce raised to 2x, we get 2ce raised to 2x. How do you find the solution? Well, we substitute. If we substitute all y's to y prime equals 2y, we'll see that y equals ce raised to 2x is the one that satisfies the differential equation. So, y equals ce raised to 2x is candidate number 3. So, that's one of the solutions to this differential equation. Up to this point, we already know that a differential equation is just an equation involving derivatives or rates of change. You may not realize it sooner and may have a hard time seeing the applications of different equations in our day-to-day lives, but it can be seen and experienced almost in any part of our interaction with our environment. Let's check some of them out. First, acceleration. When you ride a car and experience acceleration with it, you're actually experiencing a second-order differential equation of distance with respect to time. Second order is basically the formal term for getting the derivative of an equation twice. So here is the equation. For population growth, the rate of growth of a population is proportional to the population size. It can be written like so, where k is the proportionality constant. Lastly, for cooling of an object, Well, let's say you have an object and you want to model how fast an object cools or heats up. Differential equations can also be useful in this situation. The model is actually called Newton's law of cooling, which says that the rate of change in temperature of an object is proportional to the negative difference of the temperature of the object and the ambient temperature. It can be written like this, where K is the thermal constant of the object. Differential equations can also be applied in modeling electric circuits. Here's an example of an RL circuit. From physics, we know that the voltage VR across the resistor is VR equals IR, and the voltage VL across the inductor is VL equals L dI over dt. The sum of the voltages on a circuit must be equal to 0 according to Kirchhoff's voltage law. Therefore, the RL circuit can be modeled with the equation L dI over dt plus Ri is equal to E. Imagine you and a friend are on both ends of a stretched out string. You try to wiggle it, and as a consequence, a wave similar to the figure shown will be formed. Let the vertical displacement that happens on any point of the string be u x t. On each of the points in the string, force is applied like the arrow shown in the figure. As we can see, the greater the concavity, the greater the force. So we can say that the force is proportional to the concavity of the string. Well, the concavity is equal to the second derivative of the graph as a function of x, or this one. The force is equal to the mass times the acceleration, or F equals ma, a familiar equation. It is like thinking that every point on the string has a mass. Acceleration is the second derivative of the displacement with respect to time and can be written like so. And since c must always be positive, the wave equation can be written like this. Here's a short interview from an expert on the application of differential equations.
Anyway, so sa applications lang naman, when you go to SCL, you'll see a lot of researches na differential equations ang gamit, no? Differential equations naman kasi talaga also allows us to speak of physical things, most of them, no? In sort of mathematical models, right? Kasi diba, a lot of the physical things in this world, physics, chemistry also, no? Physical sciences, they exhibit, for example, changes in of properties over time, over space. And when you talk about that in these things, no, in mathematics, ang kanyang pinakakabit kagad is yung differential equations, right? For example, y prime equals y, something like that, no? Na yung y prime is essentially, you can say that that's dy over dt or dy over dx, the change of y. And then in sort of physical systems, you set what y is. For example, y could be temperature, y could be particles in the air, and then of course you let these things change over space, over time. Okay? In 130, in mathematical models, right, or mathematical methods, no, we only do it usually in mathematical form. At that is yung ating foundations is strong. And then usually when we go to researches talaga, we see, okay, pwede pa siyang gawing ganito. We can talk about it in this manner. Yeah, and these things, they allow us mathematicians, no, or when you want to talk to other mathematicians, that is, to speak of real-world things in the realm of mathematics. And that's what makes differential equations beautiful, right? Kasi it becomes on the language of math. Right?
Differential equations entail a lot of solving, but knowing about them will allow us to see the math and science behind minute details of our lives. Good luck in the classroom!
Differential, equationaro, ramen, tamagotchi, tonkatsu, Honda, Toyota, Suzuki, desu. Na!